Rectifiers used in hybrid electric vehicles. Rectifiers are used to convert an AC input to a DC output. Even though controlled rectifiers exist, they are rarely used in automotive applications. Therefore, we will only discuss uncontrolled passive rectifiers and their uniqueness aspects in hybrid electrical vehicle applications. Coming to the ideal rectifier, and this figure shows a single phase rectifier and a three phase ideal rectifier operating from ideal voltage sources. With ideal diode characteristics, the output of a single phase rectifier can be expressed as shown in equation 1. And this slide shows the ideal rectifier's top single phase rectifier circuit and output voltage waveforms, bottom three phase rectifier circuit and output voltage waveforms, where V0 is the output voltage, Vi is the RMS value of the input voltage, T is the time period of the input voltage, omega is the angular frequency of the input. The output voltage of an ideal three-phase rectifier is shown in equation number 2, where VLL is the RMS value of line-to-line voltage. Coming to the practical rectifier, in hybrid electrical vehicles applications, the input to a rectifier is generally the output of a synchronous generator, such as in series hybrid electrical vehicles or complex hybrid electrical vehicles, or an alternator. The circuit and output voltage waveforms of the parallel hybrid electrical vehicle rectifiers are shown in this particular slide. The generator impedance is in series with the voltage source and the voltage drop of the diodes is also included. It can be seen that there is a significant amount of voltage drop in a practical rectifier when compared to an ideal rectifier. The voltage drop is caused by the impedance of the generator, which is generally not negligible, different from other rectifiers connected to an infinite AC grid. Besides, there will be commutation loss due to the inductance of the generator. Therefore, the output voltage can be significantly different between no load and loaded conditions. The difference is defined as a voltage regulation. Coming to the single phase rectifier, we will use a single phase circuit to analyze the voltage regulation, voltage ripple and commutation. At no load conditions, due to the existence of the output capacitor, the output voltage will equal to the peak of the input voltage, that is V0, as shown in equation 3. When the load current increases, the impedance of the generator and the diodes will have a voltage drop of them. If the DC link capacitor is sufficiently large, then we will assume that the output voltage V0, DC link voltage, is constant. We further assume that diode voltage drop Vd is also constant. By solving root 2 Va sin omega t equal to 2 Vd plus V1, and we get theta 1 equal to omega naught t naught, and as shown in equation number 4. The analysis can be divided into two scenarios, discontinuous and continuous mode. In discontinuous mode, the AC side current is not continuous. The current starts from 0 and built up when omega t greater than or equal to theta 1. It reaches a maximum when root 2 Vi sin omega t equal to 2 Vd plus V0, as shown in equation 5. The current then drops to 0 at theta 2 less than pi plus theta 1. Coming to the continuous mode, in continuous mode, the AC side current does not reaches 0 at theta 1 plus phi. In other words, theta 2 greater than pi plus theta 1. In continuous mode, the voltage equation is as shown in this equation number 6 and equation number 7. Note that the AC input will not have current until the voltage exceeds the output voltage plus the diode drop. However, the current will continue to flow until it reaches 0 at angle theta 2. We further neglect the resistance. The above differential equations can be simplified and following the solution obtained as shown in equation number 8, 9, 10, 11 and equation 12. The output power of the rectifier must be equal to the power consumed by the load P equal to 1 by pi and so on and shown in equation 13. So the output voltage of the rectifier is V0, that is also represented in equation 14. The above expression cannot be directly solved due to the fact that theta 1 and theta 2 are the functions of V0, but it can be seen that the rectifier output is closely related to the impedance of the generator. The voltage regulation can be calculated from this equation, and that is delta V0 equal to V1 minus V0 by V0 into 100% shown in equation number 15. The voltage regulation is a function of the internal impedance of the generator and the output voltage. Coming to the voltage ripple, the derivation assumes that the output voltage is constant. However, it can be seen that the current from the AC input is discontinuous. This means that during the operation of the cycle, when there is no current from AC side, from 0 to theta 1 and from theta to pi, if theta 2 less than pi, the load current is supplied by the capacitor. However, due to the non-linearity of the current, when the load current is less than the AC side current, the capacitor still has to supply some current to the load. Therefore, we can assume that if the load current is constant and also that the capacitor supplies the current to the load 50% of the time, the voltage ripple is delta V0.